Okay, so thanks. It's a special lecture today, unusual circumstances. Events happen to be in town, so we're going to have a pleasure of having give a talk. The title of his talk is Directional Statistics of Lattice Points and Escape of Mass for Embedded Horospheres, and I made sure to tell him to introduce the subject slowly.
Yeah, 5 minutes before the lecture. I'll do that. Okay, so I'm gonna first of all start talking about directional statistics. So what is that? So imagine you have a point set, you look out in the stars in the sky, and you want to understand the directions in which you see the points in your point set. So P is going to be our point set in RD, and we look at all stars in a ball of radius T. And for now, I'm going to specialize in a second, but for now, we'll just assume that we have a general point set where the number of points in the ball of radius T grows at most like the volume of the ball times some constant. And now we'll do what I just said. So we'll have all our points and we project them down. So let me draw this in 2 dimensions. So these are our points. Look at all points in a ball of radius T. And I'll project them onto the unit spheres of directions if here's my observer. And so we get all the points projected, in this case, onto the unit circle. Yeah, so now the idea is we want to understand the distribution of these projected point sets. And in particular, we want to ask how random do these points appear? So
you have to do single page.
Single page. And how do I do that, Svetlana?
Window.
I know how to
Window.
do that.
No?
Yeah.
View, yes.
View.
Yeah.
And where do I do?
Yeah.
Single page. Great. Okay. And now I go back to full screen. Great. Thanks. Okay. So I'll denote by rho the uniform probability measure on the spheres of directions. And now to define what I mean by understanding the pseudo-random properties of my projected point set, I'll test that by placing a disk at random on my unit sphere, and I ask what's the probability of finding k points of my point set in that disk. And what I want to do is I want to scale the disk in such a way that that probability has a good limit, which means I need to make the disk so small that the expectation value of the number of points that I can find in there is finite. And this is done in the following way. So I'm going to denote my disk D by dt. It's centered in some direction B, so that's the center, and then sigma here is a scaling parameter that's chosen so that the volume of my disk with respect to my natural probability measure on there is sigma over volume BT. So ball has radius roughly t to the d minus 1, t to the d, and so I normalize by that. So if I now ask what is the number of points in my projected point set that fall into this disk D, and if I take the expectation value of the number of points, you can work out that that's exactly sigma times the number of points divided by the volume over BT. And so you see, because I've chosen the volume of the disk in this way, this number here grows like the volume. That was my assumption, right? So this number is at most finite. Does it make sense? Everyone's with me, right? So I have my sphere. I choose a disk of size 1 over t to the d roughly. I have at most t to the d points on my sphere in total. So the expectation value of finding points in a small disk of that size, as I've chosen it, is at most finite. So I'm interested in the fluctuations around this value, right? So I'm now asking, well, how many points are actually in my disk? What's the probability of finding k points in that disk? So what I'm gonna do now is I explain to you how you can now translate this question in counting points in a small disk into a very natural question about group actions on my point set P, my general point set P. And how does this work? Well, first of all, I'm going to define this cone here. So that's just some fixed cone whose sort of cross-section is a disk. And the reason why this cone will be important, you'll see in a minute. So what have we done? What I've told you so far is I've picked a random disk. So in this two-dimensional situation where we project points down and onto the unit circle, we'll just have an interval, right? My disk is a small interval. We have t squared points in my interval, in my big circle, so t squared. So remember, how do we want to scale the interval now? It should have size 1 over t squared, roughly, right? So it's equivalent of counting projected points in that little interval. It's equivalent to counting points in the sector that are now not projected, right? Because it's exactly what we do by projection. So this now will be a sector of radius t, and here we'll have roughly 1 over t. Because you scale up. Here we have 1 over t squared. And so you scale up. So it's equivalent of counting points in this blue sector that's placed down at a random angle, right? Because our interval is placed random on the unit circle, so that's now becoming a random sector, which is long and stretched. That here represents my blue random sector, and what I'm going to do now is I'm going to rotate this random sector with a rotation matrix to become a horizontal sector pointing in this direction, and then I'm going to apply a diagonal matrix, because remember, this is now t, this length here, and this length here is roughly 1 over t, so I'm applying a diagonal matrix 1 over t to this whole picture, and that gives me, if you think about it, a triangle in this case that is now more or less fixed, right? And in higher dimensions, as you see, the scaling is slightly different, but these are the right scalings, and you can reflect on this a little bit, that where in higher dimensions you get exactly that. The key observation here is that this matrix has determinant 1. The rotation, of course, also has determinant 1. And so what we've achieved here is that when we're now interested in the probability that there are k points in our randomly placed small disk, probability here means probability measure on V. You can choose this at random. It doesn't have to be the uniform measure necessarily. You can choose more complicated measures. Is approximately the number of points now in, so when I apply these linear transformation, I have to remember also to apply them to my point set P, right? Because otherwise I would get a different count, right? So I've now rotated my point set P by the same rotation that I needed to get my long and thin cylinder into the right position, apply the diagonal matrix, and now intersect with my fixed yellow triangle here, or in higher dimensions, fixed cone that I have up there. This approximate here just means I've made a little error because the cap of my cone is curved. And here, as you see, that cone has a flat cap, but as t gets larger and larger, this flat cap, curved cap becomes flatter and flatter. And by an argument that you have to do, you can show is that the probability of having a point exactly in the different set, which is a very small set, will be very small. So you need to make that argument. But for now, you can ignore that and just assume that that just works on the nose. Okay, so the important observation here is that we've transformed the problem in counting in long, thin sets into counting points in a nice fixed set. And we've introduced a group action on our general point set P.
You haven't assumed any group action to be any invariance.
Nothing yet, no. And in this generality, this is a question you can't answer. So when we now come to specific point sets, then we can do that. But let's just play around with this. So I had a very specific set here, my cone, and it's good to step back a bit and replace that just by a general test set, right? So why stick with a cone? So we'll instead of considering this very specific one, let's just think of A as a nice general test set bounded with boundary of zero measure. And so what we're really asking here is the following question. We're asking a question about a randomly rotated point set that's then stretched. We're asking what's the probability that this set intersects a general given test set A in k points. What we'd like to prove is that as t tends to infinity, remember that's our limit, right? T, the ball becomes big. If t tends to infinity, that converges to a limit. So actually you can think of that statement as a question of convergence of random point processes. So you forget about the test set. That's just one way of stating convergence of point processes. Here it would be, finite dimensional distribution, but you can make it more general and say, well, really here I have a point process, even for a deterministic set P, because you rotate it randomly, it becomes a random point process. And so we're interested in this general question of convergence of randomly rotated sets that are then pushed by the diagonal action dt. And so that's quite a natural question, I think. And what it tells you is that if we understand this particular convergence, we get all local statistics, these directional statistics, as a corollary of understanding this type of convergence by choosing the test set to be a cone test set A.
You so far haven't said much about the point set, but could I choose the point set to be all the points on a fixed shell of radius, so projecting integer points, not in a annulus, but on a, that's going to be much harder.
Yeah, exactly. I know you've worked on this, and I have it on the slide that's coming up. This is a slightly different question, right? Because you, as you say, you just restrict that, and that's indeed a harder question. So here's one example. You can take P to be generated by a random point process, the Poisson point process, and you fix it. I just said P could be deterministic. Here, let's not take P to be a random object anymore, but just a generic realization of a Poisson point process. And then you can ask this question is, does then, for almost every realization, this random rotated and stretched copy converge to a limit. And in my joint work with Andreas Strömbergsson in connection of the Lorentz gas, so this was really just sort of a little corollary of what we're working on there. And I'm sure it's somewhere in the literature. What this theorem says is that almost surely the limit will be a Poisson point process. Okay, that's not a surprise. All I want to say here is that there is a little subtlety here. So if you would take P to be a random point process without fixing it, the theorem would be trivial, right? Because Poisson point process is invariant in distribution under any volume preserving linear transformation. The key point of this statement here is that it's a little bit like an ergodic theorem where you have an almost sure convergence result. So it's a much stronger statement. And in particular, as a corollary, then you get the answer to this question of when you take your stars are on a position on a Poisson point process, you fix it, you project them onto the unit sphere, and you ask what's the probability of finding k points in this randomly placed disk. It's going to be the Poisson distribution. So no surprise here. And on the left, you'll see a little numerical experiment where this is done. So you fix the realization of the Poisson point process. So it's really fixed. Then you do the statistics and you see this curve, and that's the answer you would get for a Poisson point process. I showed this picture in John Keating's birthday conference, and I made a little joke. Maybe I shouldn't have, and I tried people to think this was random matrix theory. But of course it isn't. That is just the distribution, the nearest neighbor distribution for a Poisson point.
In dimension 2?
Yeah, this is in dimension 2 because we've taken a three-dimensional Poisson point process, projected it onto the unit sphere, where it's then a point process, Poisson point process on the unit sphere. So that's exactly the directional distribution, exactly. Now I'm going to tell you what this curve, this histogram on the right here is. We now come to the other example, which is the situation when instead of a Poisson point process, you now take a lattice in 3 dimensions, for example. So take a 3-dimensional lattice and do exactly what we've just described. We look at the directional statistics, and in an old theorem, again with Andreas Strömbergsson, we proved that if P is now a lattice, take the just the cubic lattice in Z, so ZD, you shift by some fixed vector alpha, so you get your point set. The observer sits at the origin. And so what we showed here is that as a point process, the randomly rotated affine lattice and then stretch converges to a limiting point process, which depending on the choice of alpha is a random lattice. So if alpha is irrational, it's a random lattice where G is Haar randomly distributed in ASLDR modulo ASLDZ. So for those of you who don't know what these symbols mean, it doesn't matter. It just means it is a natural object in the space of randomly of lattices with where you apply a random affine linear transformation with a natural probability measure on it. If alpha is a rational point, then you will get a corresponding random lattice, but this time the Haar probability measure on the corresponding space of lattices needs to be chosen differently. So for instance, if alpha is 0, then P would be 0, and you would just have a traditional random lattice. So the take-home message here is, if you don't know, Peter told me too late to go easy. The point is here simply, we get limits. We understand what this limit is in terms of natural objects in the theory of the space of lattices. Now, this theorem already needs very sophisticated machinery to prove for for alpha irrational, we need to apply Ratner's theorem. When alpha is rational, you actually only need the mixing property to prove this. And in recent developments, people have been able to prove effective versions for these theorems. First, Andreas in 2015 for in the two-dimensional case, and more recently, Wooyeon Kim in a very substantial paper for arbitrary dimensions. And yeah, I mentioned the work
Is that using the effectivization of Ratner or?
yes,
Yeah, okay.
yeah. So that's Kim's paper. Andreas' work uses harmonic analysis, whereas Kim is more closer to ergodic theory. And as Peter mentioned, there is an analog problem to this. When alpha is 0, you have high concentration of lattice points on spheres themselves, so you can understand, or you can ask about the statistics of the lattice points that actually lie on a sphere, if you've got enough points on them. And so that's work of Wooyeon, Rudnick, and Peter. And also there's a very beautiful recent paper, well, recent 2 years ago, 3 years ago, by Kohlberg and Lester, where they prove a Poisson distribution for the lattice points on a circle for the integer lattice. Okay.
In the histogram in the slide before,
Yeah.
why does the right-hand side look kind of off?
Because it's not the answer you get for
I see. Okay.
the Poisson point process. So that's the actual distribution. And I'm gonna tell you a little bit more about that and on the next slide. So for here, I just want to say that, so this previous theorem, as I said, it's a sort of convergence of the whole point process. And as a corollary, you get that the number of points in the projected lattice points in a randomly placed disk is given by a limit distribution. And in higher dimension, we can't work out explicit formulas for the limit distribution, but we know, for example, that there are only finitely many finite moments. So if we're in d dimensions, the expectation value is what we expect by our normalization. If alpha is rational, we get moments, eta, up to d. So the dth moment diverges. And if alpha is irrational, we get a few more moments. So that's an interesting phenomenon where we get 1 power higher. So just keep that in mind for now. Yeah, so
Is this related to some integrals on fundamental domain diverging?
exactly. And I'll come to that. So just keep that in mind. So in the case of a Poisson limit distribution, all moments would converge. If you remember the formula for the Poisson distribution, right? Here, that's not the case. So now these are the two histograms again that I've showed you, and you see the distribution really looks different. In 2 dimensions, we can actually work out the formulas for the limiting gap distribution. Yeah, I should have maybe emphasized this. This is the formula for the nearest neighbor distribution of points on the sphere. As a, one of the most natural statistics. This is the gap distribution. So now we're projecting really all the points on the unit sphere, and you can ask what's the distribution of gaps between those points, and you see those two histograms. So if it will be a Poisson point process, it will be an exponential distribution. And here it's this distribution. You can work out what the formula is. And by some beautiful coincidence, it's the same distribution that Elkes and McMullen found in 2005 for the gaps between the fractional parts of the square root n.
This is just a coincidence.
It's not a coincidence at all, but the beauty of understanding everything in the space of lattices is that you can just see why it has to be like.
I mean, the answer is not surprising maybe, but you don't have a relation between these problems.
Okay, so there's no relation between the problems except that both questions can be answered by translating them into a question of translates of, in Elkes-McMullen's case, of so-called nonlinear horocycles on the space of affine lattices. And here, it's a equidistribution of large circles in the space of affine lattices. And the beauty is that in both cases, the test that you need is a triangle. And in both cases, the limit is the same. It's Haar measured. So that's why the answers are the same. And you can make that observation without doing a single calculation. So Elkes and McMullen had done all the work for us in working out this formula. So we could just quote that. And that's, yeah, okay, don't want to go into detail, but there are many other situations where people have gone through long calculations, arriving at the same formula where they just could have looked at the interpretation in terms of space of lattices. Here, the tail is, you have an algebraic tail in these formulas, which is also very different from the usual exponential tail in random variables. So here the decay of the limiting density is 1 over s to the power 3. Okay, I really want to talk about moments. That's also related to the question Peter just asked. And so we looked so far at the question of, what's the probability that the number in our disk is equal to k. So let's just look at the etf moment and ask whether this converges. So the first moment we've already discussed. That's just the expectation value. And what I showed you on the previous slide is that by our assumption on the total number of points in a big disk growing at most like volume, we already have an upper bound for this. But we don't know the constant. Now, if we have convergence in distribution, if we understand that our spherical averages have a limit, and I've showed you two examples, the Poisson case and the lattice case, then we also get the convergence of the first moment for free because we already have an upper bound. We know the convergence and distribution, and then we're done. And that's exactly the strategy that was used in the work of Veach, Maser, Alex Esken, and in particular the spectacular work of Esken, Merzatani, and Mohammadi, but also in earlier work on quantitative Oppenheim conjecture and visible lattice points, where actually you don't know that the number of points in a big ball of radius t has an asymptotics. You know an upper bound, but you don't have an asymptotics. And so understanding spherical averages gives you that asymptotics, and that's exactly where the ergodic theory comes in. So there are some problems where you always think, oh, it's easy to count points in my point set in a big ball of radius t, but it's actually not true, right? And so this combination of upper bound plus having convergence of spherical averages is really key to solving that problem. Good. So we know the first moment if we know spherical equidistribution. Now let's look at another statistics, not the probability.
I always found that. Did you ever heard of this Ripley thing before?
Yeah, I did hear. I mean, it's spatial statistics. They do this. Of course, it's just correlating.
Forests. They look at forests. Yeah, they look at distribution of where the trees locate themselves in the forest.
So we looked at, I've showed you histograms of the nearest neighbor distributions. We talked about the probability of finding k points in a little disk. This is another one that's very popular, also among statisticians, which is always reassuring. And that's just understanding the distribution of all distances between pairs of points that you can get, right? So you're counting the pairs of points in your big ball of radius t. we assume that we don't take the equal points because that'll be trivial. That just give us zero spacing as an answer. And now we look at the distribution of distance between our projected points from our point set. And we ask how many of those are that are a distance less than s. And we have to normalize here by 1 over the average distance, right? We have n points projected onto our sphere. So the average distance between points will be 1 over n, so 1 over d minus 1, so the reciprocal of this. We divide by the total number of points, and then the question is, does this have a limit distribution? This is the so-called two-point statistics or Ripley's K function for a general point set, and here we apply it to our projected setting. Studying this kind of quantity is in fact equivalent to looking at a mixed second moment of this type, where we count the number of points in our favorite small disk with parameter sigma. Remember, sigma was sort of the sort of volume of normalized volume of our disk, times the same thing with radius epsilon. The way you can think about this, you make epsilon very small, so you sort of force one point to fall into that disk, and then you ask, well, how many more points are there in a smaller disk around it? So that's somehow what gives you an approximation to this two-point function. I can tell you later how they are related. It's just a remark to tell you that in order to study this quantity, it suffices to look at general mixed moment of this form. Now, having understood the convergence and distribution of our point process doesn't mean that we get also convergence of the second moment. This is a statement for the experts here, which I'm not going to go into detail. And so, for example, one can show that if P is a realization of the Poisson point process that I showed you, and then we project down, we look at the quantity on the previous slide, that it converges almost surely for almost every realization to a limit. And here's the limit. And now you say, okay, what happens for lattice points? Let's do the same thing for lattice points. And my recent theorem with Wooyeon Kim shows that if you take our shifted lattice points, you project them onto our unit sphere, you look at all the directions. If alpha is irrational, that's important here, we also have a convergence of the two-point correlation function. And has anyone spotted a difference? This is the formula for the Poisson point process, and this is the formula for the lattice. It's the same. So whereas the gap distributions were different, the two-point statistics can't distinguish between projected points from a Poisson point process and projected points from a lattice. That's a very subtle statement. So some people say, oh yeah, you're just counting, and it's obviously the same. The two-point statistics is a very fine statistics that usually detects sort of non-generic effects, but it doesn't here. So if you have a guy out in the forest measuring distance of trees, and they are only looking at the two-point statistics, they won't be able to distinguish in this limit, of course, whether the trees are Poissonian or coming from a lattice point, if you project down. So it has to be projected.
That's only if alpha is irrational.
Only if alpha is irrational.
You move over a tiny bit and you.
Yeah, if alpha is rational, this all breaks down. I'll comment on that in a second. In 2 dimensions, we in fact need a Diophantine condition. And that was already known in my work with Daniel Albaz and Ilya Vinogradov. And what really struck me here, I hadn't expected that we are able to prove in higher dimensions that no Diophantine condition, except for being irrational, alpha being irrational, is required. And the key points of our proof here are, of course, the theorem that I had with Andreas on the convergence of distribution, but then also escape of mass estimates, because in order to prove convergence of moments, you need to control the moment. So convergent distribution doesn't imply convergence of moments. Weak convergence doesn't imply LP convergence, right? You need to make sure that you can truncate, and what you truncate can be made arbitrarily small in the limit. And the second ingredient to show it's actually Poissonian is a Rogers type formula for the second moment that shows that it's actually the volume that you're getting for this second correlation function. We can also prove convergence of higher moments, provided, of course, that they're not so large that you are in the regime where your limiting moment diverges. Okay, and here I've just written down the Diophantine condition that we need for the moments. I won't go through it, you can just stare at it. It is a variant of the sort of famous Bruno type Diophantine condition. We didn't find exactly this condition in the literature, but it's very closely related to a extension of Bruno condition, the so-called S-Bruno condition that was invented independently recently by Unamura and Fayos and Lopez Diaz and Gaballo. Okay, let me move on. Here's just the numerical illustration of what I've just told you for the Poisson case. The blue thing is the histogram. And here, this is the lattice case for this choice of alpha. And both follow the curve that I've showed you.
Why did you choose alpha for this?
Yeah.
What was the reason for this choice?
The reason for this choice was just arbitrary. As you've cleverly observed, I could have taken anything that's irrational because this is the three-dimensional case, so everything should have worked. I shouldn't have put a particularly badly approximable vector alpha here. Okay. So now let me tell you a little bit of what's behind the proof. And I'm going to go a little bit quicker to not bore the experts and also not bore the people who are not experts and come to an end. So it's just going to be a quick outline of the main ingredients here. So the main playground is the space of lattices, and in particular, the space of affine lattices. So that space is parametrized by SLDR. So that's our first Lie group, the arithmetic subgroup SLDZ. And so the quotient here, because SLDZ is a lattice and SLDR is a good space. It's a good homogeneous space that carries a probability measure that comes from the Haar measure on G, and that can be normalized to have mass 1. And then you can extend that group through a semi-direct product construction where you take G semi-direct product RD with this multiplication law to create a group G prime, which is called ASLDR, the affine special linear group, which is essentially just volume preserving transformations, linear transformations, and translations, because we want to also be able to move our lattice by translation, right? That's why this is a natural construction, and we take the corresponding arithmetic subgroup, and then you also have a natural homogeneous space, which is now G prime modulo gamma prime. You can embed G and G prime just simply by this natural homomorphism. And so you can think of now of X, which one usually calls the space of lattices, in X prime, the space of affine lattices as a submanifold. And you can think of X prime as a torus bundle over X, because here we have the translations modded out by ZD, that's a torus. So on each point on X, you have a torus that you carry with you. And if you apply a transformation from gamma prime, the torus will feel that action from gamma. Okay. And you can define a natural right action on RD in this way. Okay, why did I do all of this? Well, because just to remind you how the proof for the convergence of this probability for this works now in our setting here. Remember, we said that the probability of finding k points in our little disk, projected points in our little disk, can be rewritten as points from our rotated and dilated point set intersecting our fixed cone. And here, as a reminder, that's how our fixed cone looks like. And now, if we choose P to be ZD plus alpha, we can prove the convergence of this random variable or this quantity here by referring to the equidistribution theorem for rotational averages on the space X prime, because X prime parametrizes all affine linear lattices. So when you rotate and shift this thing, that can just be parametrized by working directly on X prime. Now, in order to go from such a statement to the convergence of this statement, you need to choose this test function f cleverly. Normally, one assumes it's bounded continuous in this kind of weak convergence. Of course, the probability of having k points in a set, if you think about it, corresponds to a test function that will be discontinuous because you might leave your set if you move slightly. So it's a discontinuous function. But the discontinuities form a set of measure zero for the limit distribution, which is our nice Haar measure. So you can deal with that. And this type of convergence here now can be proved using Ratner's theorem. And in fact, it's a special case, what we have here, of a theorem of Nimish-Shah, who used Ratner's theorem. And Nimish-Shah's theorem is about convergence of translates of certain unipotents that are embedded in a bigger space. And again, as I mentioned earlier, effective versions of exactly that statement have been proved recently by Wooyeon Kim in general dimensions following the work of Strömbergson. Okay, so that's the convergence in distribution, but we are interested in the convergence of moments. And so in order to do that, as I said, we need to control the escape of mass. And how do we do that? Well, we want to work out this type of average. So if this function could be interpreted as a bounded function, we'd be done, because then we can just use our previous theorem. Unfortunately, as it turns out, it's not a bound, it doesn't correspond to a bounded test function, but a function that has singularity, that grows, that has singularities in the cusp of our space X prime. So what we need to do is we need to split up our integration into two parts. So we just truncate in the first part, we just say we look at the moment, but we cut it off at some capital K, which we'll take to be arbitrarily large eventually, but fixed for now, and everything else that's bigger. So if we look at this quantity, this corresponds to a bounded test function on our space. You need to believe me that, but we've truncated it and so it won't grow. And so here we can just apply our limit theorem as t tends to infinity that we had on the previous slide. We get an answer, and then as we take k to infinity, our truncation of the limit, we get the limiting moment, provided eta is small enough so that the limit is finite. Yeah, does it make sense?
Eta is fractional usually. Or is
Either
it-
can be fractional, yeah, yeah.
So-
Can be any fractional number sufficiently small so we have a finite limit moment. So that's of course cheating. That wouldn't solve our problem because we haven't shown that we haven't lost any mass, right? So what we need to prove, what remains to be proved, is that this quantity here, K larger and larger, gives a smaller and smaller contribution. So that's the only thing that we need to do to pass from convergence and distribution to convergence of moments is to control such a quantity. And when I say just, Alex has spent a lot of time working on the quantitative Oppenheim conjecture. That's exactly the just that was so important to establish those theorems in controlling the escape of mass. And if you see the recent papers of Lindenstrauss, Mohammadi, and Wang on the sort of effective versions of that, that is also a key ingredient in those papers. In our situation, the geometry is the following, and I'm gonna finish soon. Again, this is just impressionistic for you who haven't seen this. I just want to give you a flavor of the type of geometry that's involved here. What does it mean to be in the cusp? What does it mean for a function to grow in there, and how we can limit it? So the key point is to find good coordinates for the space that we're working on. And our space is SLDR, that's where our function lives. And the convenient parametrization here is the famous Iwasawa decomposition, where you decompose an element in G into a product of elements of 3 types. So this upper triangular matrix times a diagonal matrix times a rotation matrix. Here, the important thing, of course, we have determinant 1. So we'll just denote the space of corresponding space of these diagonal matrices by T. And yeah, and that's what I've written here. That's our Iwasawa decomposition. And that's the right coordinates to describe the geometry now of the space of lattices. So that would be G modulo gamma. You can say, well, if I fix a fundamental domain and I understand the fundamental domain, I understand the geometry that I need, because my function, I just need to know it in the fundamental domain and how it grows there. But unfortunately, the fundamental domain for D greater than, well, for 3, there's still a nice fundamental domain that you can work out explicitly, but it becomes increasingly intractable in higher dimensions. So what you can do to make your life easier is you don't look at a fundamental domain, but you look at a slightly larger set, the so-called legal set, that you can describe very well, and that contains a fundamental domain, and is contained only in at most finitely many translates of your favorite fundamental domain. So I've written down the Siegel set here, as the name suggests. That was written down by Siegel first, as far as I know. And it's a very simple set. You have the Iwasawa decomposition, and you have simple inequalities simply on the diagonal entries. And since we're only interested in upper bounds, that's fine, right? We don't actually need to know the precise shape of the fundamental domain. For upper bounds, the Siegel set works perfectly fine. Now you extend it to the affine lattices by adding the torus components, but you may ignore that for now. So that's the idea. So you understand the geometry of your space G prime mod gamma prime in this way. And now we make 2 key observations. This is the quantity we're interested in. We want to work out the moments of this guy. And as I've explained to you earlier already, it's just related to this rotated and stretched object. And to make things rigorous now and get a good inequality, I'm just making my cylinder slightly bigger to deal with the problem of the curved cap, you remember? And then it's fine, right? So we'll just make it slightly bigger, and we're only interested in upper bound, so that's fine. Here are a few things that you don't need to read. The second one is a slightly more interesting inequality, and that shows that the number of points to the power eta can be rewritten as a simple count of a small interval intersecting a shifted one-dimensional lattice times a weight factor that knows about eta. So the V's here are the elements in our diagonal matrix in the Iwasawa decomposition. And you see what really comes in here. So the B knows about my shift alpha. So the B knows about the shift alpha. And when we go into the cusp, some of the VIs will be very large, and these will be the critical ones. So this interval will be very small. So we're really asking questions on a small interval, avoiding a lattice point in that shifted lattice. And so when B is 0, that won't happen. That's bad. That's when we lose. But if B satisfies a Diophantine condition, it will happen rarely. Yeah, and that's what we got to play with. So there you already see how a Diophantine condition comes up. So then we turn this observation into a model function that grows in the cusp at the right way. So it majorizes our original counting problem. Well, and then we got to work to bound the horospherical average over this function. And here's the theorem that does this for you. So it shows that if you have our function, and the R refers to truncating the function in the cusp. Yeah, so we're only interested in the divergence in the cusp, so we just truncate it, because for every R we already know what happens in the complement of the cusp. So we're really only worried about the divergent part. So what this shows is that this gives us exactly what we need for every moment eta. The part in the cusp that diverges is controlled in a way that if we move the truncation higher and higher up, we get a vanishing contribution. So that's what's giving us the upper part, the upper bound that we needed to move from convergent distribution to convergence of moments. As you see here, it requires the Diophantine condition. So in fact, it does go wrong if we don't assume this Diophantine condition. But beautifully, it depends on D. So if eta is smaller than D, we don't need a Diophantine condition. And if we're looking at pair correlation, if you remember, that corresponds to the second moment, eta equal 2. So just for D equal 2, we have a problem, and not in higher dimensions. So that's a great thing here, because I love it so much. Again, the Diophantine conditions, you got to show off sometime. And then having this theorem, we can then conclude that we get convergence for every eta moment, and the limit will be the moment of the limit distribution. So that's then the final result. And indeed, we can also do mixed moments here, as long as the sum of the two exponents is less than D plus 1, we get that convergence, and therefore we also get the convergence of the 2-point correlation function. So that's where I'll stop. I have some more technical stuff here, but I hope I've given you just an idea of what the sort of main ingredients are. I haven't really told you how we actually prove the convergence, but I hope you got a flavor on in particular, the important fact that you can't just move from convergent distribution to convergence of moments. And the amazing thing here that for a reason, of course, there's a reason behind it, which is that we have a formula for the second limit moment, which is the same as for a Poisson distribution, right? So that's, I think, a beautiful observation that, of course, we knew before, we just didn't have the convergence of the moment. So that was the last missing ingredient. And I was a little worried about not having a Diophantine condition. I always thought pair correlation needs a Diophantine condition. But the reason why we don't need it, and that's coming back to your question earlier, what happens for rational alpha? The point is that for rational alpha in 2 dimensions, the pair correlation function will diverge. And that's very similar to signature, to 2 Oppenheim forms where the rational points just behave badly. They diverge. In higher dimensions, the 2-point correlation function exists for every alpha, rational or not. And in fact, if you take then, and it's never Poissonian for rational alpha, but if you take a sequence of rational alpha that approximate an irrational alpha, you'll get the Poissonian answer. So there is, if you like, a certain continuity in the limit distribution in the rationals. And that's the reason why you don't need a Diophantine condition. The Diophantine, so that's not a proof because you could have gone wrong, but we proved that you don't need a Diophantine condition, but it gives you a reassurance that we've done things consistently because you don't get divergence at rational points. High dimensions, the rational answer is much better behaved than in 2 dimensions. Okay, I'll stop here. Thanks.
Thank you. Very interesting talk. Any questions?
Can I ask the Diophantine condition is stronger or weaker than a typical Diophantine?
It's weaker. So, for instance, the standard Diophantine condition is implied by our Diophantine condition. So the Bruno type conditions are always softer. And so it's always been a great advance to be able to move from the more traditional Diophantine conditions to Bruno ones because it allows a bigger set of alpha to be included.
What are the points that's deterministic points that can you take and get this analysis?
So none so far. So with Andreas, we looked, for instance, at directional statistics of quasi-crystals,
Yeah,
like
yeah.
take the crystals tiling.
You got it? That worked.
We have only convergent distribution, but it's something I'm working on. So we don't have that type
The
of
answer
limit
is
theorem.
going to be the same.
Yes, it's always going to be Poissonian. The limit, we know the limit distribution will be Poissonian because we have a Rogers formula.
Yeah.
In that situation, if we shift, if your observer is generic, if not, then not.
Because you could take in your thing that shells, spin shells.
Yes, we can take shells. The good we can't yet shrink the shells.
Yeah, the sphere. In high dimensions, I bet you can, but in dimension 3, it's
Yeah.
So in the theorem, what kind of techniques are using? Geometry of numbers kind of stuff, or is it?
We use not so much geometry of numbers. We use a dyadic decomposition of everything that moves, and then we count. And so that's how I would describe it. Of course, it's a geometry of number type argument, but we just don't quote something. One thing I sort of regret is, I mean, I want to redo this proof using the Margulis function. So I'm learning more about Margulis functions now. But here we really, because we really have the key thing is the action of SLDZ on the torus component. So we cut everything up and then we see how SLDZ moves things around and we make sure that not too much mass accumulates in there. It's on the sort of the outline is on these last slides, but I don't want to bore you with this on this nice evening.
it's not such a nice evening. But the rain has stopped, so.
Okay, yeah, maybe people want to use the opportunity.
All right, any other questions?
Can I regard as a stronger version of like a quantitative non-divergent?
Yeah, so we don't have a quantitative version.
Like the Cranbrook-Margulis quantitative non-divergent, can I consider this as a stronger version of that?
It would be a stronger version, yeah, because we can't just use Kleinberg-Margulis non-divergence, yeah. Okay, I should say in the two-dimensional proof that I did in 2015, it was classic Diophantine approximation argument. So there we really just used the standard techniques, which was still non-trivial, but yeah. So, but here it's as a, I think more of an ergodic theoretic claim.
But yeah, I mean, let's end it and then people cannot continue to ask
Yeah.
questions. Okay, so let's thank Jens for